Day 41, Honors Physics, Energy, Problem 25. Once again, here's the diagram, and there's the bicycle. Well, make believe there's a person sitting on it at point A at the top of a hill. Excuse me, it's implied in the problem that the bike at the top of the hill at point A is starting from rest, and it coasts down. In other words, the meaning of that is they're not pedaling and adding energy to the system. In the best case scenario at point B, you would have lost no energy, or you never lose energy, but there would be no transfer of mechanical energy to heat. But with air resistance, there is a transfer of some of your mechanical energy into heat energy on the way down the hill. Well, what you do is you figure out the GPE at point A, which I found out to be 72,000 joules. By the way, you know, the person's mass is going to be 90 kilograms if you use 10 for the acceleration due to gravity. But mg, already in the mgh, is your weight, basically. So you can solve and find the mass, which you actually will need for the kinetic energy at the bottom. For example, down at the bottom of the hill at point B, you take 1/2 your mass times your velocity squared, and you get a kinetic energy of 18,000 joules. In the best case scenario, once again, that would have been 72,000 joules. That would have been a conservation of mechanical energy, which isn't the case here, but there is conservation of energy. What's missing is you subtract those two to get the answer. That's the energy dissipated to heat or to other forms of energy as the bicyclist coasts or travels from point A to point B. And by the way, the 20 meters per second at the bottom of the hill is a pretty fast speed. That's pretty wild on a bike. If you're going that fast, that's like 45 miles per hour. So that's actually a little scary if you're on a bike. Hopefully you're wearing your helmet.